We will start and start to introduce you. So if you
whenever you want, I'm ready.
Thanks. Thanks. Good afternoon to you, bon après-midi à vous, bon pomeriggio a tutti voi, guten Tag, buenas tardes a ustedes. Welcome to Paris and to the International School of Astrophysics Daniel Chalonge-deVega for this program, Nobel Lectures in Physics, I organized this year. And it's a great pleasure and a great honor to welcome today Professor Barry Clark Barish here, Nobel Prize in Physics for his decisive contributions to the LIGO detector, laser interferometer gravitational wave observatory, and the discovery of gravitational waves, which shared with Rainer Weiss from Massachusetts Institute of Technology and Kip Thorne from Caltech. Barish has a long-standing leadership career and leadership in high-energy physics and particle physics, earned a bachelor and PhD in University of California at Berkeley. His early career is associated, say, to important experiments at, for instance, in the 70s, a Fermi lab on neutrinos, and the confirmation, just to mention a highlight of the discovery of neutral weak currents, one of the pillars predicted theoretically by the standard model of particle physics, which was not said just Nobel Prize at that moment, but became later and gave in the 80s the discoveries of the boson, heavy boson, W and zeta, and meaning Gargamel, I mean the golden days of Gargamel at CERN. And so in the 80s, he was starting, associated to the ambitious effort in the setup and development of national laboratories, also in the experience of neutrino masses and neutrino oscillations, and in Italy associated also in the facilities, underground facilities, for instance, Gran Sasso at L'Aquila. In 91, as professor at Caltech, and headed the high energy physics program and group and department there. And 94 nominated PI, I should allow me to say, to relaunch the LIGO project, which he put it placed it in the advanced LIGO, and from 97 director of the LIGO project, and in his which reached the success. We know today, and from 2015, the magnificent discovery, and served. I would like also to say, served and serves as advice to community, advisor in highest national committees and boards, and international, of course, but in US to advise the Congress and President on science, engineering, and education, and continue his tireless activity, I said, and I stop here, and it's a great pleasure. I thank Barry for being here and to present this his lecture on his gravitational wave detections and understanding. He titled for us understanding our universe with gravitational waves. Thank you very much, Barry. The floor is yours.
Thank you. Thank you, Norma. I'm happy to be in, I guess, virtually in Paris. I wish I were there. It's daybreak in California, where I'm sitting, and I'm going to give this lecture. There's a lot of different aspects of gravitational waves that I could emphasize today, but I'm going to concentrate, once I kind of introduce the subject, mostly on what we potentially and what we're learning about the universe through gravitational waves. Is a different kind of radiation. We, of course, also use gravitational waves to test Einstein's equations and so forth. But today I'm going to emphasize the kinds of events that we're seeing and what the prospects are, not so much in the long range, but even in the next few years. So in that spirit, I show a cartoon of one of the puzzling events that we saw before we were turned off by the pandemic last year, giving massive more massive black holes than we anticipate coming from stellar origin, from stellar origin. And this is a puzzle, and I'll show the other puzzles that we have, much unanswered at this point, but I think where we have very good prospects as we improve the detector to pursue these areas. So first, let me remind you that gravitational waves first are a consequence of special relativity and the finite speed of information travel. The Einstein predicted gravitational waves in 1916 by basically noticing that the equations that he had for general relativity had similarity to the equations that we have in electromagnetism, where we have electromagnetic waves. And he didn't prove it, but he made the leap to intuitively to predict then, since the equations had similarity, that there would be gravitational waves. 2 years later, in 1918, he wrote a second paper on gravitational waves. And that paper, for the purpose of an experimentalist, had the value that it demonstrated that the source of gravitational waves, in contrast to electromagnetic waves, where they're made by an oscillating dipole, are made by a quadrupole. So you have to have a quadrupole moment to make gravitational waves. And of course, there's the strength, which is a separate question. So a cartoon like the one I show here of two objects going around each other, like barbells that you lift, or two objects like the moon around the Earth or the Earth around the sun, or in the case of us, two black holes going around each other, or other objects like neutron stars, create a quadrupole moment. That quadrupole moment then produces a gravitational radiation that emits outward at the speed of light. If I don't remember to say it, just incidentally, we have demonstrated in one of our events that to 1 part in 10 to the 15, the speed of light and the speed of gravitational waves are the same. Hopefully I'll remember to show you that when I come to it. Anyway, the gravitational waves then are emitted at the speed of light. And although in the original paper of Einstein, he makes the analogy to electromagnetic waves, these waves, of course, don't have the equivalent, in the classical general relativity, don't have the equivalent of a photon accompanying them. They are truly just ripples traveling at the speed of light, the same speed as light, ripples in space itself, in space and time itself. So they're radiating out. And the equation depending on how you set up general relativity. I've chosen to do it a particular way here to illustrate that the equations, Einstein did it in a different way in the first paper, but the idea is the same. I use actually the weak field limit here, but setting up the equations, the equation for general relativity looks very much like the equations we're so used to in electromagnetism for electromagnetic waves. And the little h mu nu that I have here is called the strain, and it's the quantity that we measure in gravitational waves. Since this looks like the equation for electromagnetism, it means there'll be basically plane waves that'll propagate, and they propagate at the speed of light. So in the illustration here, we have two plane waves. So far, it looks very much like electromagnetism, the speed of light. However, there's no equivalent of a photon. Nevertheless, you'll notice in the picture here that the two waves are not like in electromagnetism at 45 degrees, at 90 degrees to each other, but rather at 45 degrees to each other. And that is a consequence of the fact that gravity is spin 2, while electromagnetism, of course, is spin 1 with the photon. That's just the background. Using that, we can take and predict a lot of known objects that could give gravitational waves. They may or may not be waves that are strong enough for us to detect in our present era of gravitational wave detectors, but there are several kinds of sources. I've categorized them here just to give you a sense. First are the kind that we've already detected. That's two objects going around each other, emitting energy, radiating energy in the form of gravitational waves, therefore losing energy and spiraling slowly into each other and eventually merging. Examples of those are a pair of neutron stars or a pair of black holes, both of which we've seen, and I'll show you that. The technique that we use, I'm not going to talk very much about techniques today. To look for these is the idea of using matched templates. That is, we use general relativity to calculate different configurations of, say, black holes, different masses of the two, generate a whole slew of templates, and we test those against the data as it comes in. And that's the general technique that we use to see gravitational waves. So it's not triggered like a particle physics experiment by the beam or by an interaction, but rather a continuous stream of time frequency data that we compare with a set of templates, hundreds of thousands of templates to cover the whole phase space that are each calculated using the techniques of general relativity and numerical relativity, which took us a long time to develop, to be able to calculate and develop the templates on a computer, hundreds of thousands of them. We needed to be able to do numerical relativity on a computer, which was done only a few years before we made detections. Other examples that could give gravitational waves are supernova. That's the collapse of a star. To the extent that there's a quadrupole moment when a star collapses and gives a supernova, it will give a burst of gravitational wave energy. We know that when stars collapse and they basically give a final neutron star, or whatever the final product is, that has an average velocity of a few hundred kilometers a second, which indicates that the collapse isn't totally spherically symmetrical. So we expect to see the signals from the collapse of a supernova. However, it has to be close enough to us on Earth for us to be able to detect them again with present generation detectors. Of course, we haven't seen any yet, but it's what we look for. The third source, I'm not going to talk about these very much, except just to introduce them now so you know what they are. The third source is signals that, rather than being chirps or a burst like a supernova, are periodic in nature. An example of that would be spinning neutron stars or pulsars in our own galaxy. to the extent that the neutron star or pulsar is not totally spherically symmetric, has little mountains on it or whatever, it will give signals that are periodic. We haven't detected these yet. We search for them. I don't have time today to talk about the searches. If we search for known pulsars, the ones that we have identified with radio telescopes in our own galaxy, we so far have only seen limits on the gravitational wave signal. That has the problem that by giving a very steady radio signal, they're older pulsars. Younger pulsars are probably more likely to have a sizable quadrupole moment, but it's very difficult to do anything approximating an all-sky search for gravitational waves. So we're limited by either looking at limited sources or by computing in doing this. The advantage of it, if once we detect them, and if you ask me what we're likely to detect next, I think it's probably pulsars. If we detect them, it has the advantage of being like other physics experiments where you can keep measuring and pursue it afterwards. So once we've identified a pulsar, we'll be able, with improving detectors, with taking data, to be able to analyze it and understand, for example, the features of a neutron star. Lastly, and maybe the most romantic, would be to see signals from gravitational waves that come from the early universe. The stochastic background, which again, we look for but haven't seen. We're at very high frequencies, so it's probably not the ideal way to see the gravitational wave stochastic background, but that depends on the features of inflation. I won't have time to talk much about that. So far, we only have limits, but hopefully in the future in our detector, or possibly the ones in space, or pulsar timing, which I'll mention before we finish, we'll be able to see the early universe signals in the future. Okay, so I'm going to now talk just briefly about how gravitational waves get detected, what they do. So a gravitational wave comes through space from wherever the origin is and comes to the Earth. As it comes to the Earth, it's a wave, as I said, very much like an electromagnetic wave, but has the features that what it does is to stretch and compress space-time itself. And the amplitude of that, for the sources that I'll show, the black hole sources, which is just a good one, that little h that I showed at the beginning is a very tiny number. It's 10 to the minus 21. That basically is why it's so difficult to detect gravitational waves. The effect is so small. The little h corresponds linearly to how much space is distorted. The change in length shown if I had a circle of free masses, as I show here, the change in length or radius is little h, the 10 to the minus 21 times the size of the circle. So that number is incredibly small and was the big challenge in detecting gravitational waves. Why is it so small? I don't know, of course, but what it means is that if you think of space itself, which gets distorted by gravitational waves, and think of it maybe a little bit like a material, it's very stiff. So it doesn't get distorted very much by the passage of gravitational waves, which maybe is a good thing, but difficult for us. So the stiffness of space-time means the effect is incredibly small. I illustrate the size of the effect in this little picture at the bottom, which is the same circle with free masses on it, and a gravitational wave goes through it. When a gravitational wave goes through it, it distorts it by delta L, first vertically and then horizontally at the frequency of the gravitational waves. And that effect then, if I had a circle of free masses that was 1 meter, the size would be 10 to the minus 21 meters. That's an incredibly small number to measure. And for that reason, simply for that reason, the detectors, whether it's the one in Italy or ours or the one being built in Japan, are, instead of meters in size, are kilometers. So we make it kilometers in size, which changes the 10 to the minus 21 to 10 to the minus 18 that we have to measure. And that's still an incredibly small number. 10 to the minus 18 meters is the size of a proton. So the picture I show here is the simplest idea of what LIGO or gravitational wave detectors are. A laser beam sends a beam in from the left side. It hits a mirror, which divides the beam into two parts, one going vertically, the other going horizontally. To the extent that both arms are the same length and there's no gravitational wave going through, the light goes vertically and horizontally and reflects off a mirror, comes back at exactly the same time. If you invert one compared to the other, they'll cancel. And the sensor that I show here in a simple-minded way sees no signal. What we're trying to see is illustrated like the picture when one arm gets a little longer or a little shorter than the other, causing a phase change of the light in one arm compared to the other arm. We measure it more and more accurately by having lots and lots of photons and lots of very fancy optics, which I don't have time to describe today. Instead, I show on the right side here, in the simplest possible way, what the challenges are and why it was so hard and took so long to detect gravitational waves. Many of you, or most of you, probably used an interferometer in freshman or sophomore laboratory and saw fringes. Maybe you could see to a fraction of a fringe, a tenth or something. Fancy interferometers might see to a hundredth or maybe even a thousandth of a fringe. But we have to do 1 part in 10 to the 12th of the wavelength of the light that we use. So that's the accuracy that's needed to get the 10 to the minus 18 meters that we need to detect. To do that, was an incredible amount of development of tricks, amount of light, and precision of the optics that is built into the interferometers that we have developed, and that took a long time to get interferometry to be that accuracy. That was the #1 challenge and involved a lot of inventions of how to do interferometry over a period of 20 years or so. The second big challenge, there's others, of course, but the second big challenge is that we're doing LIGO on the surface of the Earth. But it turns out that the Earth vibrates much too much for us to see these small effects. So in a sense, we live here on the Earth. We have to put our detector on the Earth, but we have to isolate ourselves from the Earth entirely, basically float the detector over the Earth so it doesn't feel the vibrations of the Earth. I won't talk much about the technology, but basically that was the second big challenge because we have to, again, isolate ourselves at the frequencies that we're looking for gravitational waves to 1 part in 10 to the 12th from the vibrations of the Earth. Those were the two big challenges. It was solving the second one in what we call advanced LIGO that enabled the discovery of gravitational waves in 2015. So without going through any of the experimental details, that gives you at least a picture of what we needed to do. The project itself started in 1994, and that's when it was approved by the National Science Foundation and funded to build the detectors. From the beginning, we were building 2 detectors, and we had 2 groups, Caltech and MIT. We proposed it to the National Science Foundation. We proposed that one of the sites be in the Owens Valley, a short drive from Caltech, and the second one being in southern Maine, a short drive from MIT. They approved the project, but they chose to rotate it by 45 degrees and put it in the state of Louisiana and the state of Washington. That meant we couldn't drive to it so easily, but it did mean that we had 2 senators from the two states who were very strong supporters of LIGO, and that mattered through the years. These two detectors are 3,002 kilometers apart. At the speed of light, it takes 10 milliseconds to go from one to the other. So if a gravitational wave came first through Hanford, Washington, and then to Livingston, it would take 10 milliseconds later before it was seen in Livingston. If it came first through Livingston and then Hanford, it would be 10 milliseconds earlier in Livingston than at Hanford. And of course, if it bisected the two, it would arrive at exactly the same time. So thinking of the picture I drew before, that we look for some effect, we ask that that effect be coincident, occur in both these detectors within plus or minus 10 milliseconds of each other. And depending on which one came first, we can see something about the direction. However, having only two, as anyone who knows who triangulates, any two detectors, we can't do a very good job of telling where it's from. We need three. And it was the addition, which I'll point out, of the Virgo detector in Italy that has enabled us to point much better in the sky, which will be crucial for much of the science that I'll indicate later. This is just a picture of the two LIGO detectors. They're in very, very different topographies. High desert for Hanford, Washington, and a commercial pine forest for Livingston, Louisiana. The detectors themselves, however, are kept identical. When we make a change of even a simple circuit in one of the detectors, we do exactly the same thing in the other one to keep them identical. And when we keep them identical, the performance is exactly the same, almost exactly the same. So those are the two detectors. The length of those arms is the 4 kilometers. And the corner is where all the optics and lasers and so forth go. Using a detector like this is what you end up pictorially as what limits it. Let me point out that all the limitations are technical, not physics. So by physics, I mean something that mocks gravitational waves themselves. That's in contrast to, say, experiments which I've done much of my life on particle accelerators. If you go to CERN and look at the discovery of the Higgs boson, it was a little teeny effect on a very large background. The background in that case is very, very much and very well studied physics. So the ability to understand the shape of the background is from physics. It can't be eliminated. It's just understood from all the experiments that are done. And then statistically, the little peak at 125 GeV is seen over that background. However, it's been much harder to pursue more sensitively following that, except by having more and more data at CERN, because the background is physics. The background in the case of gravitational waves is technical and noise, and those can be reduced. So basically, since we discovered gravitational waves, we've been able to improve sensitivity to see gravitational waves by quite a lot, and we will continue to do that in the future because we're not limited by physics. We're limited by our technical ability to reduce technical backgrounds. Those backgrounds are shown on this plot here, and we're able to see anything above the lines that are shown, which are all the different backgrounds, from KT noise in our mirrors to the shaking of the earth, to how good the vacuum is, and so forth, to how many photons we have, which is the shot noise. The shaded area is the area where we're sensitive. So you'll notice that this goes from tens of hertz to 10,000 hertz. We're sensitive, if you look at the left scale, at something like 10 to the minus 21, the scale that I looked at. So anything that comes into the shaded region is where we're above any noises, and we can detect real signals. The real signal is shown here. So showing the real signal, this is as the different colors are as a function of time. And you'll see it has the same shape. This was in the early 2000s. I just like to plot, which was us basically running the interferometer, figuring out what limited it, whether it was some technical noise, power of the laser, or shaking of the earth. And we'd improve that, then we'd run again, and it got better and better until it got to the red on the bottom, which matched a little line that you can see with where the February 15th points to it, which was the calculated ultimate sensitivity we could get to if we controlled all the noise backgrounds. And that was the situation. And each time we ran on these, we searched for gravitational waves, didn't find any, then improved the detector and searched again. These were at a level that was already beyond any previous gravitational wave detector. So even though it took us a long time, between 2000 when we started running this and 2015, before we finally got sensitive enough to see gravitational waves, we were able to set astrophysical limits so that graduate students and so forth that worked with us could get theses. I'm going to only show you one technical picture because it's the one that matters in terms of our final detection. And that is how we got the ability to detect gravitational waves in the very end was to reach the factor of 10 to the 12th that I mentioned earlier in isolating ourselves from the Earth. That was done originally by passive shock absorbers. The passive shock absorbers, like the shock absorbers in your car, are very fancy ones. When your car goes down the road and you go over a bump, the high frequency of the bump gets by the shock absorbers absorbed and moved to lower frequency where it doesn't bother you, and you smoothly go over the bump. We made basically in LIGO the world's fanciest shock absorbers, 4 layers of them, and that got us to beyond where I just showed you the sensitivities, but not to the sensitivity where we detected gravitational waves. In terms of the numbers that I gave you earlier, with passive isolation, 4 layers of passive isolation, we got to about 10 to the 10th rejection of the shaking of the Earth in the audio band where we work, not to 10 to the 12th, which I indicated was what we needed to detect gravitational waves. We did that in what we called advanced LIGO by adding another feature, and that is by adding active seismic isolation, detecting what the residual motion of the Earth was that was getting through the passive isolation with seismometers, detecting that and then pushing back against it with active actuators. So basically that's what was added, that and reaching the ability to split a fringe to 1 part in 10 to the 12th was what we needed to detect gravitational waves, which we did in 2015. What I'm showing here in the top on the right is how well, on the left was how well we did in initial version of LIGO before we did improvements. We improved in what's called the advanced version by making a higher power laser, by making better test masses, bigger and better polished test masses, better optics. And I just mentioned better seismic isolation by adding active seismic isolation. On the right, more or less is a status report. We basically improved, as I've shown in the arrows, from the upper one, which is what we had in our first almost 15 years, 12 years of initial LIGO, to advanced LIGO by the technical improvements. And we still have more to improve to the bottom line. The red and the blue looking like on top of each other indicates that the 2 interferometers, when they're set up right, work the same. You can see that the improvement at low frequency is much better than at high frequency. It's a log scale. So we improved a factor of 100, and that was 10 to the 10th to 10 to the 12th at low frequency. That was what enabled looking at seeing the gravitational waves from black holes, which are heavy and only come into our detector at low frequencies. So we improved a factor of 3 at high frequencies, a factor of 100 at low frequencies. I'll just point out one other thing. We measure an amplitude, not a power. So when we increase the sensitivity a factor of 3. We actually look a factor of 3 further out in the universe, and that's a factor of 27 in how many objects we cover in the universe, or the volume. And likewise, when we gained a factor of 100 by active isolation, that improved our sensitivity by a total of a factor of 100 cubed or 1,000,000. And that's why we could detect gravitational waves in just a week of running on the new detector when we couldn't do it in years before that. So in September 2015, 2014, we saw what's shown on the left here. And that's the first detection of gravitational waves. That first detection of gravitational waves, what's shown is 0.2 of a second going from left to right. And the scale of the vertical scale is in units of strain, which is 10 to the minus 21. So you'll notice that we're seeing wiggles that are a fraction of the 10 to the minus 21 that I indicated on an early slide. You notice by eye that the top and the center one look a lot alike. And in fact, if you put them on top of each other, they basically look the same if you slide them slightly with respect to each other, actually 7 milliseconds, 6.7 milliseconds. So that is basically what we're seeing, and what's figure number 1 in our discovery paper. I like this version better in the sense that I've shown the same thing in the top band. On the left is the Hanford signal, on the right is the Livingston signal. The next panel is the calculations of what the merger of two black holes would look like using Einstein's equations, classical relativity on the left, and the very final merger using numerical relativity. And you'll notice that they look very much alike. And this is with no cuts on the data, nothing done, that's raw data. And if you subtract one from another, which is the simplest way to see if there's anything about data, you get the third pane, and it just shows wiggles going up and down. That's how well we do the measurement. A time frequency plot is shown on the very bottom. So this is why, on the basis of just a single event, we could make such a convincing case first to ourselves and then the physics community that we'd seen gravitational waves. The waves themselves can be written down in detail in terms of usually what's called a chirp mass. That's what I've shown here. That enables us to get a lot of information by measuring just, say, a single event, but by measuring the details of the wave that I've shown. This is the first order term. From that, you can tell the ratios of the masses, the spins, what the redshift is, the amplitude tells you how far away it is. And the second term, which I didn't show here, you can tell if you're accurate enough, something about whether the two objects are precessing and so forth. So there's a huge amount of information, including sky location, that comes from just the analysis of the waveforms of these two objects. Okay, that's all background. Now I'm going to show you newer data. This is the basically performance of the detectors once the Virgo detector got added on. We had a technical problem in LIGO of a problem with one laser, so that there was a slight difference in this running between the Hanford and the Washington interferometers, just a technical difference in what the power was of the laser. And so the two on the right show you the range, how far out we could see a neutron star in spiral with the two. That's our equivalent of measuring like luminosity at LHC. The one on the left, the weaker one, is the Virgo detector. So it turned on in 2017, but is not as sensitive as the LIGO detectors. Nevertheless, for helping determine direction, it adds all that we need, and that's what I'll show you. So it's not as sensitive, even today. It's a factor of 3 less sensitive than the LIGO detectors, mostly because we're a couple years ahead in adding features. but that is immaterial in getting the direction. We just need triangulation, having 3 detectors rather than 2, and the details of the events we can study with the most sensitive detectors. This is basically the history since the first detections. So 01 means observational run number 1. In that first run, we made the first detection and then eventually saw 2 more events. We ran that for about a half a year. Then it's just like I showed you for the improvements in initial LIGO. We made some improvements, but not that much. But in the second run, we saw 8 events. So we had a total of 11, all black hole mergers. And in the third run, we made some rather significant technical improvements in the laser power and in handling scattered light and several other technical things. And you can see that the number of events has gone way up. We were terminated slightly early by the pandemic. You can see that it goes almost to the top, but we presently have about 70 events. This is the online number, and we have about 70 events. That's enough to start trying to understand things and see what we see beyond the first events. This is just an example of the black hole mergers. You can see that the black hole mergers now vary in the little pictures here. Each one is a different black hole merger when I'm showing it. Two masses coming together and making a heavier mass, and the totals shown across here for seeing the many, many events. These are the signals seen from neutron stars electromagnetically. So these are very heavy. In general, the mass is heavier than is easily explained from astrophysics. Basically, a progenitor mass that presumably decays to give a black hole when it has a stellar collapse is hard to be heavy enough to make these because basically stars are unstable if they're too heavy unless they happen to be in some part of the sky that has low metallicity or there's some other feature, for example, that the black holes don't come from them or that they've been dynamically made. So these various things are what we're trying to understand by looking at the features of a large number of events now. This is just to show, instead of the little wiggles or different events, looking at the little wiggles in different events, you can see they look different, and each of those we fit and see. And along the way, we saw one event that was quite different. All of these black hole events are heavy mass. They barely get into our frequency range because they're heavy, and we see them for a fraction of a second, 0.2 of a second for the very first event. We then saw an event that was in our detector for more than 2 seconds, rather than 0.2 of a second. And tens of seconds rather than 0.2 of a second. And that's shown down here. That was the first example of a binary neutron star. And that event basically opened up for the first time the possibility that we can actually combine information. And most of us feel that the real future, other than the physics future, understanding general relativity, is in doing what we call multi-messenger astronomy. And this is maybe the very first event, the birth of it, that is detecting some phenomenon in the universe with electromagnetic radiation, with gravitational radiation, and hopefully with neutrinos, and using all that information together to understand the events. An example can be the stellar collapse, a supernova. A supernova, the very first thing that happens is gravitational when it collapses, and that's the signal that's seen by gravity. The nuclear physics happens when it comes together, and that can give you the information on the nuclear physics of very, very compact objects. And then finally, the shock wave makes electromagnetic signals, which is what we presently see from a supernova. And so that's an example of multi-messenger astronomy. For us to do multi-messenger astronomy, we have to add another feature to LIGO. And that feature is to be able to tell that with some accuracy that we see something important enough to ask astronomers to turn and point their devices at where we see something in the sky. That means we have to be able to analyze for gravitational wave signals, which are hard enough to detect very rapidly. And we have spent a lot of effort doing that to develop candidates, tell their sky location by seeing them in all three detectors, or at least two, and then alert astronomers in a matter of minutes, up to 30, but often less, and then run a more detailed analysis. And hopefully we're accurate enough in the alerts, the first ones, that it was worthwhile for astronomers to turn, whether they see something or they don't. We basically presently have to say that what we saw was not an alert, was not a real phenomenon once we analyze the data about 20% of the time. So 80% of the time when we give an alert to the astronomers, it's something that holds up as a real event. This will all get better. We presently have two LIGO detectors in the US and the Virgo detector in Italy. We also hopefully will soon have a Japanese detector, which is being built in the same mind as the Kamioka neutrino experiment. And they're trying to turn it on now. It's the first detector in the world that's trying to be cooled to cryogenic temperatures. We'll see how that goes. And we're building a third version of LIGO in India. That should be ready in the mid-2020s. That will enable us to go from the situation in the upper left-hand corner here of how well we can point in the sky to the lower right-hand, where anywhere, when we have the 5 detectors, anywhere in the sky, we'll be able to locate well enough anything we see to be able to tell astronomers in a small enough circle where we see some event. What's shown here is just to illustrate with only the 2 LIGO detectors, we could only see bands in the sky that are shown for several of the black hole events here. And once we added the Virgo detector, we went from roughly 1,000 square degrees to tens of square degrees in our ability to see something. That's good enough to have astronomers look. And for black hole events, when I drew this, there were 10 only, but for black hole events, no electromagnetic counterparts have ever been seen, reported. But then we saw an event, the one I showed you, that was much, much longer in the apparatus, meaning lower masses, and reconstructed to be 2 neutron stars. That then we could reconstruct where it came from, because it was seen we had the Virgo detector as well as the 2 LIGO detectors to see them. And by when the signal arrives temporally, we could see which one it was. With that information, we were able to locate where it is on the sky, as shown in this picture here, and it was also seen by the Fermi satellite. And using other astronomical techniques, actually the galaxy that it came from was located, and that's been used for the analysis of that event, even, for example, in using one single gravitational wave event to determine the Hubble constant. What you see here is basically a time frequency plot on the bottom left from LIGO. The data above that is the light curves from the Fermi detector at different energies. And the difference between the LIGO time when it merged, which you can tell by the line that goes through it, and the start of the GRB signal in the Fermi satellite was about 1.7 seconds. The distance this was from the Earth when we reconstructed it in LIGO is about 140 million light years. In 140 million light years, if the difference between the 2 signals is 1.7 seconds, that means that they were the same, the time of flight from the origin of the merger to us was the same to 1 part in 10 to the 15. And in fact, even the 1.7 second difference is the difference between the fact that LIGO is measuring the gravitational effects of the merger, and of course, it's after it merges that the nuclear physics effects that would be seen in the Fermi satellite come about, which is 2 seconds later. Using the fact that Fermi satellite and LIGO saw this, and Virgo, we were able to then confidently alert the whole astronomical community. This is the first true example of multi-messenger astronomy, where the signal was strong enough, confident enough, that basically roughly half of the major instruments in the world pointed and looked at it, covering everything from visible and infrared light, radio, X-rays and gamma rays, and even neutrinos. There were signals seen in all of these. Unfortunately, not the neutrino signal was too weak and wasn't seen. So that was analyzed, and you can see the signals developed at different times in different frequency bands. This fit a phenomenology which had been published for the merger of 2 neutron stars called a kilonova, and which I won't go through in any detail, but it fit it fit that quite well, including the light curves and colors and so forth. And this basically is also a test of a nuclear physics effect that we don't really have well constrained, and that is our processes in nucleosynthesis. So basically this had a simple conclusion, which is kind of a nice one, which is a puzzle for physics and astrophysics, is how is it that heavy elements were produced in nature? How is it that gold and platinum, for example, got into the earth? We know that the universe is mostly made of hydrogen and helium. We know that a source of heavy elements is the supernova, or collapse of stars. And so when they collapse, we get a supernova. But our process in a supernova, which is very symmetrical, really can't make very heavy elements, but it's been what's been blamed. We now see that the heavy elements could have been made by earlier versions of neutron star collisions. And in fact, the numbers work out quite well that, for example, the main component of producing maybe our favorite metals that are in the earth, gold and platinum, were made by neutron star mergers in the past. In fact, if you take our neutron star merger and apply that, phenomenology, that our neutron star merger produced about 100 Earth masses of gold. So previous ones made more. Okay, now I'm going to go into the future a little bit and give you some sense the last few minutes of where this is going. I showed you the increase going up, which will continue in terms of number of events. As we go forward now, we will improve that, and I'll show you how much we expect in the next couple of years. But first, let me talk a little bit about the 80 events or 70 events that we have. For those, we're doing phenomenological analysis, which I won't report on yet because it's too soon. For example, the distribution of the black holes, to try to understand more about what the origin is. Was the origin come from products of heavy stars? Did it come from some dynamical processes? Was it even primordial that they came from? Understanding the distributions in the mass, the distance from the Earth and so forth gives us handles on that, but I won't report on that. Instead, one thing that we've done with our first roughly 80, 70 or so events is look at the ones that don't fit the simple picture. They may end up being nothing but the fact that we made some mistakes, or they're strange in some other way, or they may be indicative of new science. So we've analyzed what we call exceptional events, and I'll just report on a little bit of that. So we've seen exceptional events of various types. What I show here is one that has the following features. We know that neutron stars are roughly 1.4 times the mass of the sun. A distribution of the range of binary neutron stars is shown here at something like 2.75. Each one is 1.4 times the solar mass. What we see is an event with our code number on it, which is more than 3 solar masses for the product of the two. So what is this? We don't know. The combined neutron star is greater than any of the neutron star binaries that have been seen galactically. So that's one such event. We also see an event that where the ratio between the two masses is very large, factor of 10, the factor of 9. This is a great test for numerical relativity, by the way, because it's very hard to do the numerical relativity when the mass difference between the two objects is very high. But in this case, the secondary mass, that is the mass that it makes, ends up not being the mass of a neutron star, not being the mass that's consistent with what we think the lowest mass can be for black holes, but rather in between. So this is a second event, just to give you a sense. A third event is very, very heavy. This is 150 times the mass of our sun. We know that we've seen events which already are hard to explain that are tens of solar masses. This is 150 solar masses, but because it's so heavy, it barely gets to high enough frequency to enter into our sensitive region for LIGO. And so what we see is these wiggles here that don't look like the first events that I showed you, because we only see the final, if it's a black hole merger, we only see the final part of the merger itself, the coalescence. And so basically that's shown here for the LIGO, the 2 LIGO detectors, and the somewhat weaker signal, but seen also in the Virgo detector. Is that a black hole event? If it is, it looks like you're just seeing the merger part, but we can't really constrain it in the same way by fitting it, because we don't see the whole wiggles that you see coming in to this event. So we see for the first time an event that's extremely heavy. We see an event that's further away than we ever saw before, 7 gigalight years away. And that is an event that is where the final black hole is about 85 times the mass of our sun. So we're seeing that. And in the future, seeing things further away is a big emphasis of where we hope to go. And we've seen a possible electromagnetic counterpart of that event that was far away. So it has been reported. That's the first time that anybody's reported an electromagnetic counterpart for anything other than our neutron star event. So these are just, we're not drawing any conclusions, but the emphasis of what we're doing today, which is kind of a lot of fun, and that is looking at the events for the exceptional ones. As we move into the future, we have a whole program that'll improve the LIGO detectors over the next decade. We presently are running at what we call advanced LIGO. We have one more run, which will come this coming, would have been this calendar year, but it's pushed into sometime early next calendar year because of the pandemic and our inability to do work close together. And we have an improvement program beyond that, which will come in about 2025. And each of these are sizable steps in frequency. Eventually, it'll be time to build a new detector. And that's being looked at in both, and proposed actually, in both Europe and in the US. I show the European version of what they would like to build here, called the Einstein telescope, because it has a lot of the features that you could use to make a yet more sensitive gravitational wave detectors. First, it's bigger. So it's 10 times the LIGO size. It's, in their case, 10-kilometer arms instead of 3. It's deep underground. Going deep underground gets rid of the shaking of the earth much better. And it's a triangle configuration, which allows you to run the beams counterclockwise and clockwise. It's cool to make it to have less thermal noise. And it has special optical configurations to concentrate with more accuracy at low frequencies or at high frequencies. We have a different version, which would be on the Earth's surface. So what the next generation might look like, we're not sure yet. The designs will happen over the next few years, but it's possible to go easily to envision going to a next generation detector in the 2030s. If we do that, then the sensitivity is shown here. The very top one is basically the data where the data is that I've shown you. And we'll be able to get to the next line down in the improvements by next year. Finally, to something called A+, which is an improvement beyond advanced LIGO. We call it advanced LIGO plus, which adds some features optically like squeezed light that enable us to do even better. At that point, we've done about as well as we can with the present generation of detectors. And then we go to the next detectors. I've shown here the American version of the next generation detectors, but it's very similar in sensitivity to the Einstein telescope that I showed you. What is the big step in going from here to here? It's basically, in my mind, the fact that, for example, we can see the black holes, if you look on the right, all the way to the edge of the universe, but it's the ability for us to begin to do cosmology with gravitational waves. So the science will be, for the first time, not just astrophysics with gravitational waves, but cosmology with gravitational waves. This just shows the redshift possible once we add the Einstein telescope or the American detector. Lastly, as I close, let me just say that everything I've talked about is what we've done in LIGO, what we're doing in LIGO, what we will do in LIGO. That covers a frequency band that I show on this plot here on the right. But very much like astronomy, that's not the whole story. In space, they're developing a laser interferometer space antenna, LISA, which will fly in a European mission, will fly in the mid-2030s. And that covers a different frequency band, 10 to the minus 2 to 10 to the minus 2 to 10 to the minus 4 hertz. At yet lower frequency, there's a timing experiment looking at the fact that pulsars are very good clocks. And if a gravitational wave of low frequency goes through and you monitor a whole bunch of pulsars at the same time, you can see the effect at very low frequencies. This gets us near the place where we can see signals from the early universe, for example. So in the future, very much like multi-wave astronomy, we can look forward to doing multi-wave gravitational waves. So this is the picture of the LISA detector. This is just the idea of the radio signals from the pulsars. And with that, I'll end. Thank you very much.
Thank you very much, Barry, for this outstanding lecture. In 1 hour, traveling of the universe of astrophysics with gravitational waves. And it's a real challenge. You succeeded and very clear. And so, as usually in this session, in this school, we have time, if you are not too tired, we have some time for questions, comments from the audience. So I always give the audience first the possibility So if you have, the audience have, participants have questions, points, comments to address to Professor Barish, please raise your hand and activate the microphone to be allowed to pose, to formulate a precise question, please. So it was very clear, and I don't see. So perhaps, so I think there is one question here. Please pose your precise point or question to Professor Barish, please.
You're muted. You're muted.
Stefan,
Yes, okay.
I see
Thank
here.
you.
Yes.
Thank you very much, Dr. Barish, for this very interesting and understandable lecture. I have a question about LISA. What's the current state of LISA? Will it really be realized? And if so, and regarding this enormous dimensions of its arm of about 1.6 million miles each, which accuracy do we need in space, and how do we achieve this accuracy?
Yeah. Well, first, will it be realized? It is funded, and it's funded by the European Space Agency. An unknown is whether there will be part of a contribution from the US as a minor partner. It's a European mission. That awaits the results of the decadal study of astronomy in the US, which will be coming out soon. I'm confident that that'll happen, but the mission doesn't depend on that. Some of the instrumentation does. Is the technique is somewhat different. I don't have the numbers in front of me. The technique, as you say, is not to do interferometry at the level that we do it. They actually send a signal. There's receivers and transponders. So the accuracy needed isn't the same between the different arms. They're very far apart. The hard part technically is to have free masses. So to have free masses inside the satellite so that they're not dragged somehow. And that was tested in a preliminary flight maybe 2 years ago, where it succeeded at the level that's needed for the technology for LISA. So they had a test flight called the Pathfinder. It was only one instead of 3 satellites, but they tested basically the ability to put the instrumentation and make it function at the level required for LISA in space during this Pathfinder mission. So there's a lot of confidence that you can do the technology at that level. As far as I know, the timescale the fastest timescale is 2032. Usually space missions take longer than you think, but it's about that timescale. We just parenthetically, most people think it'll be the mid-2030s when that flies, and we would like to have the next generation experiment on the Earth on the same time scale. So when I showed the very, very last slides, our idea is to hopefully have a transition between LIGO, Virgo, and the next generation of detectors on the Earth at about during the time period that LISA will fly, about 2035. That's our dream.
Thank you.
Ours isn't funded.
Thank you. Thank you very much. Are there other points? Paolo, please activate your microphone.
Thank you, Norma. Thank you, Professor, for the clear explanation. I'm not an expert of gravitational waves, so I have a simple question. The light goes at 300 kilometers per second in empty. Is it possible to have a situation in the universe where the speed of the gravitational waves is not that of the light in the empty? Or this is absolutely constant everywhere, no matter what, always 300 kilometers per second?
Yeah, it's always 300 kilometers. Maybe there's going through a dense region where there's black holes or something, but that's such a small part of the universe that yeah,
Right.
it's the same.
It's not like the light that can be slower in some.
No,
minutes.
because the density of objects is just so small, and the universe is mostly space.
Thank you.
May I?
And by the way, yes, and by the way, with your observation of gravitational waves, you are able also to put the limits to the mass of the graviton, even if we expect the graviton is massless, but it's precisely connected with that, with the velocity, also the velocity of, and you have limits on the
Right,
mass of the
right.
graviton.
The way that's done is by taking the waveforms that I showed and adding a dispersion term.
Yeah.
And if you put a mass in, you're going to have a dispersion term. And that term just changes the waveforms enough. And we have a limit. I think
Precisely.
it's a very good limit on the mass of the graviton.
Yeah.
Of course,
you.
this is a classical graviton. It's not somehow what we need for quantum gravity.
Absolutely. So other questions or points, comments? I don't see from the audience. So perhaps just briefly, because it was very, very clear. I mean, just in the programs you have now with LIGO about the population, say, or distributions of what astronomers said for population, of distribution of sources, besides black holes, are you said targeting other objects, or at which kind of redshift are you targeting more? I mean, from the point of view of scientific programs.
Yeah, let me reflect on that just a little bit. We have now about a little under 100 events of black holes, and so what we're doing with those is looking at the distributions of everything from masses to distance and so forth. But at the present time, we really don't go to any large Z at all. So to go to large Z, we need the next generation detectors. So what we get with the next generation detectors is starting to move in the direction where we can do that. Why is that important? Even for what we've observed, it's important because there are three different, in the literature, there's three different explanations for these heavy black holes that we see. I didn't say it very clearly maybe, but these black holes were unexpected astronomically because of the fact that you don't know how to make them. So that it was expected that heavy stars made black holes, but they would be somewhere between 3 and maybe 10 solar masses. We see them in tens of solar masses and up to 100. So how were they made? There's at least three different ideas on the table. One is that somehow there's regions of the universe that are low metallicity. So if they have low metallicity regions of the universe, a heavy star can be more stable, and therefore you can make black holes. The second is that maybe there's regions of the universe that are more dynamical, there is more density, where black holes could have eaten each other up, if you want, and grown up into heavier and heavier ones by starting from light black holes. But of course, you have to have enough density to do that. Third is, coming from particle physics is the most intriguing, is that they're actually primordial. So that they have maybe even something to do with the dark matter. And how do you distinguish those? There's no clear way, but what you need to do is have distributions that aren't just localized, which is what we have now. And so going to larger redshift would be a big step in trying to understand the origin of even these black holes, let alone other things that we'd like to look for.
Yes, thank you. Very clear, and I precisely with what you said. I mean, in the final part of your answer, I I completely agree that the issue of the origin of massive black holes, which I mean is not completely understood and is not clarified till now. The avenues which have not been explored work doing that is the seeds of these black holes or the origin of these black holes from dark matter. And that is very important because, after all, dark matter gravitates and is particularly important in the early universe. I mean, in the early universe, or in the early stages. And so these are waves too could be a really, really very important also for particle physics. So
Yeah.
For every, I mean, for so to more theoretically explore, which has not been exploited so far too much, start to be. And the other point is, I mean, just to, I don't want to keep too much your time, but the other point is I saw just a
Unfortunately, you're breaking up. So your sound.
On the possibility of cosmic string populations of cosmic strings and found bounds on G mu. G mu about 10 minus less than 10 minus 15. I don't know. I mean, it's recent. I mean, it's LIGO collaboration, and I think. I mean, having. I mean, in the early time, study. I mean, just explore this. If the possibility of these objects, topological defects, could be in the universe and so on. At the time, I mean, in the 80s, it was with cosmic microwave, the bands were G mu less than 10 minus 6, 10 minus 5, I mean, which give for mu, I mean, the linear density or the tension for of the order of granonified energies, I mean, in the phase transition, they could. So in any case, I mean, I don't think these objects could survive today. I mean, it could be disintegrated in some phase transition in the very early universe, as you know. In any case, it's very interesting to see how much the constraint was pushed with LIGO. I mean, to have this 10 minus 15. I mean, it was. It's incredible. It's incredibly good. I mean,
right. And I mean, it's very difficult because we work at such high frequency. And the lower frequencies would be better. I think once there's LISA and LIGO in space, of course, the even lower frequency work with the pulsar timing array will help. So we, in the future, I think, can do much, much better. At present, although 10 to the minus 15 is a nice number, impressive experimentally, it's basically, it takes very radical kinds of inflationary models to get anything even approaching that size. So we have to get much better than that, probably, to be able to see the early universe signals.
Yes, and that exclude also some bounds that G mu bigger than said the bounds were around. So that constraints perfectly. I think that the most, I mean, the most challenge are very, very important. It would be with LISA to combine, with LISA to succeed to say something on the gravitational waves from inflation.
Exactly.
Because with that, I mean, having also the prospect, we have what today we know about CMB and polarization, that will be something very, very, I mean, it's a real future. It's a real,
Yeah, as you mentioned CMB, of course, I hope there's a big hope, of course, that the next generation of CMB experiments can start to see the polarization from gravitational waves.
So there are many, yes, there are many points, and the last perhaps is the observatories in India, and in Japan going, I mean, advancing as you expected, or more or less, I said.
Yeah, in Japan, they've been less conservative, and they've made the big step, which we all want to make sometime, to have the detectors be cryogenic, to be cold. One of the limitations of LIGO is that we work at room temperature. The problem with being cold is the act of making a detector cold means you have to take the heat out. Can you take the heat out without shaking the mirrors? That's a very big difficulty. And does the optics at low temperature well understood in terms of the material science? What should the mirror's material be made of, and what should the coating be made of? What we've been doing is a lot of research and development to determine what's the right temperature, the right materials, and so forth for the next generation detector, which would be cryogenic. The Japanese have jumped, and they've made their detector cryogenic, and hopefully they'll succeed. And they picked sapphire for the material without doing all the studies that we're doing. Sapphire has the difficulty that it's at very, very cold, very low temperature. So it has to be at very, very low temperature. And there's not an ideal coating that matches the sapphire to make it reflective. But they've done it with sapphire. They have the techniques to pump and make it cold. And hopefully they'll succeed. They're in the process of trying to make it work as we talk. So in the next few years, we'll see. And I hope they succeed. And we're in parallel doing a more systematic R&D study to determine what's the right temperature, what's the right materials. And in terms of India, we have the site in India, and we're starting to build the infrastructure, the buildings, the vacuum system, and so forth, which is what I call the infrastructure. We expect the Indian detector to be ready about 2025. So it's 4 years from now. Yeah. And it should be at least as good as the best of the two other LIGO detectors. And by at least as good, it's not because we're putting anything in it that's not in those detectors, but rather we're so busy taking data with the other detectors, the two in the US, that all the improvements can't be really tested and made to work. While the Indian detector can be made to be as modern, have all the improvements in it. So it should, when it turns on, be at least as good as the other two LIGO detectors, and will help us in positioning, especially covering the Southern Hemisphere.
Thank you very much. I mean, it's very, very complete landscape you give us on this. It's a real, I mean, I should say for my generation, I mean, it came a revolution. I don't know if a revolution, but something which seemed perhaps not seen by my generation. I mean, at this age. So it's really fun, outstanding. And if you allow me, I mean, very shortly, just I should say, I remind me the two in some sense historical points. The this as you said, you clearly said that the background, I mean, what the challenge or you have for gravitational waves is non-physical. I mean, it's just the noise, and then as opposite with what is in experimental particle physics, the acceleration in which the backgrounds came from collisions and something which need to be physically studied. Now, the vacuum you have in the detector also needed, I mean, as I understand for the detection, this because of the fluctuations, I mean, the very, very small amplitude you have to detect, you have to inject some vacuum, a exquisite vacuum from the electromagnetic fluctuations in the
¿Ya
detector,
están subiendo?
which is
¿Por dónde los vas a hacer empezar? Donde sea.
which is the said a quantum detection. I think it was at the time. I mean, I remember in the 70s, this quantum non-demolition. I mean, Braginsky. I mean, this preparation of the vacuum for the detector with exquisite states, which, by the way, the name was not continued to be used as was in fashion at that time.
Right.
But in fact, it's very, very important in the quantum, in modern quantum theory of information, in the quantum information theory. It came with other name, but it's precise. I mean, precisely. The concept is that. So I want just to, because you, of course, you knows about that, but I think more younger and younger even use it.
So the effect that Norma is talking about is actually a physics effect. So when I said that we're not limited by physics, it's true presently, but eventually there are what she called quantum non-demolition effects. We have the easiest thing to think about conceptually right now is that we get limited. We can't just increase the number of photons, which gives us better statistics, because as we increase the number of photons, that increases the pressure and the fluctuations of the pressure on the mirrors themselves. So that in order to do that now, we have to change the features of the light itself by using what is called squeeze light to change the waveforms to not put pressure in that affects us. And we're already required to do that. So basically the limitation from what she called quantum effects we're starting to get to where that's an effect. So what I said earlier, that we're just limited by noise, you rightly correct me, is we're getting to the point now where at least that effect is a serious and also interesting effect.
Yes, and also it's very interesting by its own. I said for quantum, for quantum physics, quantum optics, quantum information is entangled. I mean, quantum microscopic entangled states. It appears very interesting. I found.
It's also macroscopic. It's seeing quantum effects on huge mirrors. So it's
yes. So it's something which, for quantum physics, I found is very, very interesting. I mean, modern quantum physics. So the last point I will, I mean, very, very, I take profit. I mean, you are here. It's just one historical point. In fact, I was, many people pointed out, but it was of course, was Einstein and great general relativity and his beautiful prediction. But in fact, I was to the source of the papers by Henri Poincaré, in particular, you know, Poincaré, in particular, not just the published, the little note published in proceeding in the notes of the Academy of Science of Paris, but what is called the memo, what he published in the mathematical, in the journal of the Mathematical Circle of Palermo, which in Palermo, in the south of Italy, which was very important journal at that time, and Poincaré was also a very, very good mathematician, and he published there a very strong paper where he posed the problem before Einstein of how to extend Newtonian gravity. I mean, he knows all the physics at the time. We was and how to extend Newtonian gravity to relativistic theory, because Lorentz and in fact he formulated the even before Minkowski, the four-dimensional space-time. Formulated the Poincaré group he called the Lorentz group, I mean, to make it formal, and then he computed to the order of V over C squared the correction to Newton for gravity. I mean, he called on the gravific waves, and which are the gravitational waves. And that, I think, is very important point, I mean, which show how pioneering was Poincaré, but also how the ideas were at that time. And I think it's not because Poincaré, here in particular in France and others, was so good for other domains of physics and mathematics and dynamical system, chaos and so on, is more known for that. But at this point in gravitational waves, I like it very much. I mean, just to have how the ideas evolve, how these concepts come, and how the concept was formulated, which was really impressive. For me, very impressive. I had being in Italy, I had the possibility before this was digitalized to see the source in the archive of Palermo. And I took the time to go to the source and to understand what a really very, very important work. I just wanted to say.
Thank you.
I wanted to say that. So with
great.
that, I want to just to close, if you allow me, to thank you what in this program, I mean, as you know, perhaps the school have two medals. One is the Chalonge medal, which came from the foundation of the school in '91. And the first to got the medal was Chandrasekhar, who inaugurated the school in '91 in Sicily. And then after, it was too few samples of the medal. So Bruno Pontecorvo, who was a great supporter of the school and came, got one of the first samples of the medal, and then the Nobel Prizes in cosmology, who were from the beginning in the school, and when it was in 2006, and with the success of that, the medal I have here is Chalonge medal, and is you can see in the web, and there are a riverside with the European mountains and Alps, and this is because Chalonge also wanted climbing. And what is interesting here is that he was at the Jungfrau Joch station, 3,000 200 or 300 meters in Swiss, where it was a scientific station, where it was a blanket for cosmic rays, and Chalonge with his spectrograph for measurements of stellar spectra, and avoid the ultraviolet, first measurement of ozone. And this station was one ancestor of the CERN. They are before also Perrin, then after Joliot-Curie, Pierre Auger came there, and I have also the memories of Simpson from the Monitor of Neutrons, who was there. So the saga of cosmic rays, which were the astroparticle physics at the time, came from there, and Chalonge was, for astrophysics, one of the great friend also of Sikiki and so on, of Lackett. So this medal, as all Nobel Prizes coming to the program, I offered to you, even virtually, but I hope you will come to Paris. I mean, I made the invitation to come to Paris because I know you come to Europe. I mean, when there are the good conditions, of course. So you have the medal, and this is the French Mint, exclusively for the school. The French Mint, the Maison de la Monnaie de Paris, who coined for us the medal. And the second medal, yes, it's exclusively for the school. And so that's the reason why I have now the samples, because they were exhausted. And there is a rich history. We have these medals, rich scientific history. And the other is Ecole-de-Vega medal, one of the pillars of the school, a theoretician, and crossed all levels of theoretical physics, from mathematical physics, integral system, particle theory, and inflation, cosmology, dark matter, worked together in the school, and this died in 2015 at the age of 66. And the medal and the school is now with his tribute, and also this medal, which is also for science with great intellectual endeavor and a human face, and gentleman of science, the recipients of the Chalonge-deVega medals are ambassadors of the school. So for me, you are one of these examples. The school have very, very high the values of science, the values of the school, and so please consider, if you like to present more work, or what you would like to present. The school is at your disposal, and you will have an audience from here, from international audience, and so the school is open to you. Consider the school a home. Thank you, Barry.
Oh, thank you very much, and thank everybody. I wish I were in Paris. It would be much better, but this is the best we can do, and I'm very happy to participate today.
And we are very, very happy to you presented. I said so clear and deep lecture. Really.
Well, thank you.
Thank you and congratulations. Bye-bye.
Bye, John Rosa.
Bye.
So
Okay.
please, yes, you can switch off when you want. I mean.
Okay. Bye, everyone, and thank you for your patience, and it was great. Bye-bye.
Bye, Barry. We need to take care. take care. I mean, what this time could do.
Thank you. Bye-bye.
Bye-bye. So, bye, Paolo.
Bonsoir, Norma, à la prochaine. Merci
À la
beaucoup.
prochaine. Alba, Alba, do you hear me, Alba? ¿Me può sentire?
Era collegata.
Sono collegata. Mi
Sì.
sentite? Ah, ok.
Sì, sì,
È fantastica, è stata fantastica, veramente.
sì. Veramente è un... È
eccezionale.
è
Ciao,
un...
ciao Gian Rossano.
Hello, Alba. How are you?
Norma, ti ricordi Gian Rossano, Giannini?
Sì, Alba, io mi ricordo tutto.
Iron memory, very nice talk, very good organization, Norma. I really enjoyed it. Congratulations to you too. Ok, bye bye. Bye, Alba. Ciao.
Questa lecture veramente è stato una masterpiece, un'opera maestra,
Straordinaria.
Una opera maestra, una veramente sto cercando il nome, cercando il nome, non voglio dire Leonardo, voglio dire un Michelangelo. Un Michelangelo dell'onda gravitazionale, un'opera maestra veramente.
Veramente, sì, sì.
E devo dire anche che non era così associato per la gente della gravitazione. Il suo nome non era che veniva associato sempre al progetto. Veramente è un grande, è un grandioso e molto con questa umiltà. È veramente...
No, ma certo, ma le persone grandi sono anche semplici, eh?
Sì, sì, ma voglio dire che era il suo nome non veniva associato sempre per la gente, diciamo così, che era associato alle onde gravitazionali quando lui ha fatto... questo è la forza della fisica anche, viene come... Io l'ho voluto marcare anche questa, perché è stato vicino di tutti quelli che hanno avuto i premi Nobel con le particelle, le heavy boson, quando è stato lì, io l'ho menzionato, Gargamella al CERN, tutto, tu hai visto, le neutrini, e le oscillazioni dei neutrini che hanno avuto il premio Nobel. Lui è anche veramente una persona straordinaria, un fisico veramente.
Molto tranquillo, piacevole.
Sì, e come spiega?
Alla mano.
Alla mano
pochi prene di distanza.
è talmente, non so, ha talmente conoscenza di queste cose che le trasmette in una maniera così assolutamente, insomma, non so, sì, dire chiaro è poco, ecco, ma le trasmette
sì, ma voglio dire che questo si nota il fisico, perché io ho ascoltato, guarda, quante volte ho ascoltato queste lecture in Gravitational-Wave.
Sì, certo.
E devo dire che, guarda, questo è un master.
Sì.
E quello, diciamo, è la forma che a noi, è quella forma che noi vogliamo con questa, no?
Certo. Insomma, bene, sempre grazie per questa opportunità, Norma.
Sì, questo stanno E stanno molto messaggi che vengono della gente che dice un incredibile, straordinario, straordinario speech, straordinario talk. So, mi piace Alba che ha potuto collegarti perché non ti avevo visto, mi avevo visto a Paolo, dico Alba vendrà, sì.
No, sai che sono sempre di corsa. Senti, si può mandare l'invito anche a questa mia collega Silvia Vernetto, perché lei è un'astrofisica molto brava e insomma
E l'invito perché?
per le prossime conferenze.
Che se iscrive
Ma dice che le viene fuori il late inscription. Probabilmente bisognava iscriversi all'inizio. Se si iscrive adesso...
Sì, ma con il late penso che oggi ha ricevuto tutti quelli, anche quelli che ricevono il late inscription, sì, c'è il posto, ha ricevuto.
Non lo so,
late...
so che mi ha chiesto e io appunto...
No, il late inscription è per dire che è un late inscription, ma se ha ricevuto la risposta è perché viene iscritta, il suo email viene iscritto e oggi l'ha ricevuto quello che tu hai ricevuto.
Ah, ho capito, vabbè, glielo dirò.
E tu le dici che ha ricevuto oggi e ieri anche, perché si invia a quelli iscritti, lo ha ricevuto.
Sì, va bene, glielo dico. Va bene.
Norma, ti devo salutare, io mi incammino. Buon soirée.
Va bene.
Au revoir, good evening everyone. Bye bye.
Bye Paolo, ci vediamo. Sì, molto piacere di rivederti.
Ciao.
Grazie Norma,
Ciao.
a presto.
Sì.
Presto.
E quando si è registrata?
Credo ieri, oggi o ieri. Adesso glielo chiedo.
Se si è registrata oggi o ieri, ha ricevuto un mail che diceva late registration. Late registration vuole dire che
che non è esclusa, non lo so.
Che non è esclusa.
Di
tutte maniere ha ricevuto la...
Ho capito. Adesso glielo
Ha ricevuto. Sì, ha ricevuto. E se ha ricevuto è per venire, ma tu l'hai visto partecipare? Non l'ha visto?
No, perché mi ha telefonato lei dicendo che non è, appunto, si vede che lei ha letto questa late description e ha pensato che non poteva.
Sì, ma ha pensato, ma dopo ha ricevuto il collegamento, ha ricevuto tutto, vuole dire che si è ricevuto il link Zoom è per collegarsi, perché quelli che non si iscrivono non lo ricevono.
Ma
Spiego?
adesso lo chiedo, può darsi che non l'abbia visto,
Alba, noi non possiamo andare...
No, certo, a cercarli. No, ma adesso glielo spiego, insomma, va bene.
Ha ricevuto tutto.
Va bene, glielo spiego. Allora, a prestissimo e insomma, sempre veramente eccezionale. Va bene.
Sì, dopo ho ricevuto, io già concludo, ho ricevuto quello che tu mi hai mandato, tutto, le foto della sessione lì, è molto interessante.
Cerco altro adesso, ne cerco altre adesso.
No, ma diciamo per qualcuna dove c'è tu.
Ah, vabbè, ma non ti preoccupare.
Io ti ho detto perché quello tu l'hai organizzato lì, è giusto, tu hai messo tutti gli altri. Ma...
non importa, comunque ne cerco altre perché sono sicura di averle, devo solo guardare meglio. Insomma,
quella che io ti ho detto che tu già hai messo, tu hai identificato quella che io volevo come foto perché così la ho più grande.
Certo. E non so se la trovo in JPEG, ma comunque si può prendere da lì faccio fare a qualcuno, insomma, si può
Sì,
prendere.
anche se non è JPEG, ma
Sì, sì.
una foto più grande, un
Vale.
formato più grande, se non JPEG
Sì.
non importa, ma un
Sì,
formato
questo
più grande.
si può fare. Adesso
Sì, sì.
cerco e te le mando. Va
Sì,
bene.
sì, sì,
Mm.
dobbiamo, allora dobbiamo moltissimo, questo va benissimo, possiamo un altro giorno, possiamo discutere quando tu vuoi, Alba.
Magari parliamo, ci mettiamo, facciamo noi, tra di noi,
Sì,
di come organizzare qualche...
quando ti può chiamare?
E adesso, guarda, da questa settimana non tanto, ma magari la settimana prossima ci facciamo una videoconferenza.
Sì,
Poi. Sì.
no, al telefono, al
Al
telefono.
telefono, per me è meglio ancora, certo, sì.
Sì, più facile.
Certo.
Allora facciamo così perché non c'è la prossima settimana conferenza.
Va bene, così siamo tranquille, va bene.
Allora, un forte auguri.
Grazie, grazie. Vedo ancora Monsieur Sèvres, quindi tanti saluti anche a lui.
Ah, perché ha visto il team, eh? C'era Monsieur Sèvres, Monsieur Sirani, c'è tutto il team, eh?
Certo, certo. Va bene.
Allora, Alba, un forte abbraccio e vediamo di parlare la prossima settimana.
Ah, Monsieur Sèvres, buongiorno. Buongiorno.
E tu non vuoi mettere il tuo video, Alba?
Il mio video, aspetta, vediamo se funziona. Eccolo, buongiorno. Ci sono.
Sì.
Bonjour. Bene.
Bellissimo.
Va via. Sarà la connessione. Eccolo qua.
Comunque, io metterò fine al registration perché